about not an integral. Why would we, what's so great nowadays with partial sums? Do you have anything that you could use to get a partial sum pretty accurately and quickly and easily? Computers, right, and calculators. So the idea of a partial sum, don't, just because it's not mathematically elegant to have the sum of the first 10, it is very practical to let a computer add the first 100 numbers or 1,000. But what mathematicians care about is, does that series, does that give you a formula that's going to actually be convergent or divergent? Because if you add the first 100 and it goes to infinity, that's not going to help you, is it? If it goes to, like, you know, a tidy convergent sum, adding the first 100 will be useful. So what we want to look at is, when we do this infinite series, we want to know if it converges or not, because then we just use the computer or calculator to find the partial sum, and then we know, you know, within 100th or 1,000th, whatever we want to know, we can find that. But if it diverges and we add the first 100, it's not very useful. Does that make sense? That's the big picture. Okay. So they've got a couple one you're familiar with. 1 plus r squared plus da 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 r to the n minus 1. What series is that you're familiar with? And you should be familiar with this one. What's that? Geometric? Yep. Common ratio. We talked about that earlier this week. Okay. And what we did there is we, this actually shows where this formula came from, and I'll let you look at that. We did that in Honors Pre-Calc. Okay, all said and done. The most important thing you need to know about a series is, let's take the classic. 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot, 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 1 over n. This is not arithmetic. We're not adding the same. It's not geometric. We're not multiplying by the same. It's something completely different. It's the sum as k goes from 1 to n of 1 over n. I guess we could say n equals 1. And so this is what we call a harmonic series. We'll get familiar with it. But it looks like, what would the last term be if we went to infinity? What's the limit as n goes to infinity? 0, right? And so if you think about it, that's pretty important, because if we're going to add a bunch of terms, what did the last term better be if we're going to get a sum 0? It's the only choice we have. If it goes to 2 and stays at 2, what's 2 plus 2 plus 2 plus 2 plus 2? Infinity. So what does the last value have to have a limit? It has to go to 0. So one of the prime techniques that we're going to have for evaluating where the sum of a series, I always think sum of a series sounds kind of funny. That's sum of a series. That's going to be equal to, has to be equal to 0 to continue. This is my step 1 in analysis of whether that thing is going to converge. Got to go to 0. One more time. Hold your arm like this. Take your finger on the left and then go dot, 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 like ones. What if they were always 1? Is that going to converge? 1 plus 1 plus 1 plus 1? No. How about go down to a half and then go half, 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 half? Is that going to converge? No, it'll still go to infinity. So what does that have to do to eventually get a total sum? 0 every time. Every time. And so that is my first, on a test even, I'm going to ask you, check to see if this series could possibly be convergent. You just take the limit. And if you get any number and as you go to infinity other than 0, it's not going to work. Seems almost too easy, doesn't it? Take a look at this one. You have n squared over 5n squared plus 4. And you start putting numbers in. You could put a 1, and you're going to get, like, what is that, 1 over 9. And then the next one's going to be 4 over 24, right? I think. And then it'll just keep going and going and going. Will this series converge or not? Not, because what's the limit as n approaches infinity of n squared over 5n squared plus 4? 1 over 5. It's not very much, but because it's 1/5, it's going to be 1/5, 1/5, 1/5, 1/5, which is going to diverge. So the very first test that you do is you take the limit as n goes to infinity. And if it's not 0, it diverges. Doesn't that seem too easy? Yeah. I like too easy. And now we come to the second thing that you're going to do. Let's say that you found that the last term went to 0, but you want to know whether this converges or not. Not every one that goes to 0 converges. So we do something which we call the ratio test, or in French it's D'Alembert. It's not D'Alembert, but D'Alembert is French. And what he did is you can see the proof here using the formal definition, but essentially what happens is you take the next term over the previous term and take the limit as that goes to infinity. And if that ratio is less than 1, it's going to be convergent. You're going to love these. If it's greater than 1, that means it's doing what? It's going up. It's going to be divergent. And then if it equals 1, it's annoying. It's frustratingly annoying. Can't tell. I like to say can't tell. It's inconclusive. Formal definition, u of n plus 1 over u of n minus L. If we analyze that, get a common denominator. If the limit goes to 0, we just get u of n plus 1 over u of n, and that's my epsilon. Okay, and so this particular test is what we use to see if the series converges or not. It's a real quick one. Let's do 35 kind of as a group here. Let's first of all take the limit as n goes to infinity of n cubed over 3 to the n. What's that going to be? Can you? Yeah, it is infinity over infinity. So what are you going to have to do? L'Hopital's. You're going to do this a bunch of times until it all of a sudden grinds down to 1 over, it'll be 3n squared, and it'll be 6n, and then it'll be 6 over something with an n in it. Eventually, it's going to go to 0. Eventually. All right. Now, we're going to use the ratio test, and here's how the ratio test works. You need to make a statement that all terms are positive, and that has to be listed whenever you use the ratio test. So if you see ratio test, you're going to write all terms positive. It's a requirement because if you put in a 1, 2, 3, 4, 5, aren't they always going to be positive? Yeah. So then you go the limit, then approaches infinity, of, you just put an n plus 1 wherever you have an n. So it's n plus 1 cubed over 3 to the n plus 1. And then it's divided by, I'm just going to multiply by the reciprocal, 3 to the n over n cubed. Do you want me to write that out a little clearer? Let's go. A of n is 3 to the n over n cubed. So a of n plus 1 is going to be 3 to the n plus 1 over n plus 1 cubed. Is that a little clearer? A little clearer? So now I'm going to rearrange these. I'm going to put my n plus 1 cubed over n cubed here. This is going to be 3 to the n. How many 3 to the n's do I have if it's 3 to the n plus 1? 3 of them. 3 to the n's. The 3 to the n's cancel out. And so we're left with the limit as n approaches infinity of n plus 1 over n cubed times 1/3. Now, what's this going to go to as n goes to infinity? What's that going to go to? What's 1n over 1n? 1. So this is going to go 1, right? And what's 1 cubed times 1/3? What's that? 1/3. There you go. This is the limit L of a of n plus 1 over a of n. Now you look, is L less than 1? Yep. Oh, what's a greater than? Why? Because it's all terms positive. Yeah. That's why we have to make that statement. So we get that. So if L, we do have L as 1/3. So therefore, series converges by ratio test, the RAT test. What do you think? It's okay. Let's do a couple more. Here is 1/2 plus 2 factorial over 2 plus 4, 3 factorial over this mess. You have a of n is equal to n factorial over 2 times 4 times ... times 2n. What will a of n plus 1 be? Well, it'll be n plus 1 factorial for sure. And then this will be 2 times 4 times ... times 2n times 2n plus 1. Did I lose anybody there? Did you say yes? I just put, wherever there was an n, I put an n plus 1. Wherever there's an n, I put an n plus 1. But with this part here, we still keep these, and then we multiply by the next one, which will be 2n plus 2. So then when I take, we want to say all terms positive, which they are, right? So requirement of ratio test, the limit, kind of like that L'Hopital's where you had to have the indeterminate form, a of n plus 1 over a of n. So a of n plus 1 was n plus 1 factorial over 2 times 4 times ... times 2n times 2n plus 2. And then we're going to invert and multiply 2 times 4 times ... times 2n all over n factorial. You like that factorial, don't you? Anne's shaking her head. I agree. It's a little nasty. So you have the limit. N approaches infinity. I'm going to rewrite this as n plus 1 times what? N times n minus 1 times n minus 2. Put that over n factorial. And then in the top here, we're going to have, looks like, going to have 2 times 4 times ... times 2n all over 2 times 4 times ... times 2n times 2n plus 2. Okay, what's going to cancel out? N factorials. What else is going to cancel out? A whole lot of these, right? All the way to here. So it looks like we have the limit as n approaches infinity. Look what's left. N plus 1 in the top. What's in the bottom? 2n plus 2. And so what will that limit be as n goes to infinity? 1/2. Isn't that cool? So this means, therefore, since 1/2 is between 1 and 0, and all terms positive, I should do this part again. The limit as n approaches infinity of a of n plus 1 over a of n is between 1 and 0. There we go. And all terms positive. The series, as ugly as it is convergent by the rat test. All terms positive for this one. So let's list it. A of n is 2n plus 1 over 2n minus 1 times 1 over 3 to the n minus 1. The a of n plus 1 is going to be a little uglier. It's going to be 2n plus 1 will be 2n plus 2 plus 1 will be 2n plus 3, because it's 2 plus 1. 2n minus 1, it will be 2n plus 2 minus 1 will be 2n plus 2 minus 1, which would be plus 1. And then this will be times 1 over 3 to the n plus 1 minus 1 will be just 3 to the n. So when I take the limit as n goes to infinity of a of n plus 1, which is 2n plus 3 over 2n plus 1 times 1 over 3 to the n, then take the reciprocal here, which will be 2n minus 1 times 3 to the n minus 1 over 2n plus 1. You go ahead and simplify that. And we'll finish this here quick. So you get the limit, n approaches infinity, of 2n plus 3 times 2n minus 1 over 2n plus 1 times 2n plus 1. And then in the top, it's going to be 3n times a third over 3 to the n. Is that little 1/3 very important? That little 3 to the negative 1, that little tiny thing? Yeah, because everything's going to cancel out. This is all going to go to 1, so you're going to be left with 1/3. And so you'll have the same thing as that for your final statement.